So
Okay.
hi, good evening. This is Saurabh Srivastav, and I welcome you all to this seventh iteration of Cyber Jagrookta Diwas. This is an initiative that IITISM is taking right now, and it happens on every first Wednesday. This time we have to change the timing slightly. We have kept it in the evening slot, but the idea is that we invite certain people, certain certain researchers who are working in the field of cybersecurity to come and share whatever they are doing with us. And this is more of a talk where we are going to look at the fascinating world of quantum computing and how things are going to change once we actually, if we people, go forward and build some more quantum computing power, right? Today we have Dr. Tikaram Sanyashi with us, and I'm just gonna introduce him briefly. So Dr. Tikaram Sanyashi has recently completed his PhD from the Department of Computer Science and Engineering, IIT Bombay. He works broadly in the area of cryptanalysis, and he has put his focus on quantum computing, on the quantum computing involved with and the the idea of state of the art security systems when they are going to be operating over these so-called quantum computers. It's a very fascinating thing to know about. And prior to joining the PhD program, Tikaram has also served in the capacity of a faculty member. Currently, he is working as a postdoctoral researcher at the Information Security Research Development Center, ISRDC, at IIT Bombay. And as I've already said, it's a topic that is something that most of us really want to know about. I'm not sure how many of us know in detail, so it would be a very exciting talk. With this, I'll just hand over the podium to Tikaram. Tikaram, over to you.
Yes, thank you, Professor Saurabh, for such a nice introduction. So, in my today's talk, I will be covering post-quantum cryptography, and uh, the technique using which we can restrict or work on post-quantum world, or if in post-quantum, if post-quantum technology comes into the reality, and also cover a little bit about homomorphic encryption scheme. And I will complete my talk with one of the encryption scheme that we have taught in my PhD thesis. So my name is Tikaram Sanyashi, and I'm currently working in ISRDC labs in the Department of Computer Science and Engineering, Department of Computer Science in IIT Bombay, under the guidance of Professor Bernard Mages and Virendra Singh. So whenever, yeah. So in today's world, we usually use encryption to protect our data from data breaches. And basically TLS and HTTPS are used to ensure that our communications is communication is encrypted, and we talk to authenticated servers. In HTTPS, web browsers use public key to check websites validity and establish a symmetric key to further do the communications. And the goal of using encryption in HTTPS is to stop hackers from try to guess the key used or further communications, whatever users and server do between them. And so in today's transport layer security or HTTPS, we usually use RSA, Diffie-Hellman, and elective curve to ensure security. However, the security of these encryption schemes broadly relies on the interactability of integer factorization problems and discrete logarithm problems. Now, one question comes to our mind that will RSA and Diffie-Hellman or ACDC electric discrete logarithm problem will remain safe forever? So to answer that, we have to understand that these problems are secure only for classical computers and not hard enough for quantum computers. So if tomorrow quantum computer comes into reality, then they will break these encryption schemes and codes whatever we use to protect our data. So in quantum computers, there is a source algorithm which can be quickly factor prime numbers. So RSA problem can be RSA and Diffie-Hellman problem can be brought using source algorithm. Similarly, there is an Grover's algorithm which can search database of order n in time square root of order of n. So using these algorithms, we can break today's hard problems, and basically whatever encryption schemes we use for today's for keeping today's information will be broken. So as shown in the slide, AES 128 and RSA 2048 will not provide adequate security in the quantum world, unlike the classical world. But if we double AES key to say 256 key bit length, then it will give us 128 bit security, even if we can even if there is a Grover's algorithm in the quantum world. And in case of RSA, even if we increase key size by say a factor of 7.5, then it will have little more effect on little effect against the quantum computers. And in the tables, I have shown that the hardness of these hard problems against classical computers as well as quantum computers. In the classical world, AES 128 bit gives us a security of 128 bit. However, in case of quantum worlds, it can only give us security of 64 bits. However, this scenario completely changes for RSA. RSA, when we choose key length of 2048 bit, then it gives us security of 112 bit. But in case of when we go to quantum world, RSA 2048 can only give us security of 25 bits. So we can say that even if we increase the key size of RSA problem, then in that scenario also RSA cannot hold the security. Also, 99% of the cryptocurrencies, whatever we use today, are based on elyptic curve cryptography. And if quantum computers comes to reality, all of these will be broken, and whoever breaks these cryptocurrencies will be billionaire, basically, gets all money. So these are some depressing informations, but is there any information which is satisfactory to us? So this question can be answered by these points. So if quantum computer comes into picture, then it will help medical research to grow faster. Also, traffic jams can be predicted very first before they can occur, because of the basically first computation nature of quantum computers. Also, debugging of millions of lines of codes will be done within a second. It also helps in data analytics and so forth. Now, so we have talked about quantum computers and its advantages and disadvantages. But now the one question comes to our mind is, what is the current status of quantum computers? So currently, IBM has a quantum computer which is named as Eagle, which has 127 qubit computation power. And in the next year, that means in this year itself, by the end of this year, IBM is planning to release 433 qubit quantum computer. And by the end of 2023, it is planning to release 1121 qubits quantum computers. However, it has been proven that to be crack a RSA algorithm, the quantum computers needs to have 20 million qubits. And it can break just the RSA 2048 just within 8-hour computation time. So here qubit means the same as data of bits. In case here qubit means same as data of bit that we use in classical computers as quantum computers. Qubits are basically used for in quantum computers. So now naturally one question comes to our mind. So if RSA to break RSA 20 million qubits are required, and current state of art is say I mean next year we will have 1,000 around qubits, then why we should worry? So this question's answer can be answered using this slide. So in basically defenses or satellite communications, we use some info, we share some information which should be kept for 30 to 40 years. That means it should be secure, secure, and nobody should be decrypt this information for the next 30 to 40 years. But say after 10 years, quantum computer comes to the picture, then this can be, if somebody stores this information now, and after 10 years his quantum computer comes, then that could be broken. So the information will not be remain secure for 40 years. It will be broken and recovered within 10 years itself. So we should be worried about that. Also, the huge amount of investment is going on in quantum world. So USA has already invested 1.2 billion USD. Similarly, China and India has also invested almost 1.06 billion years. So with this much investments, we can surely assume that quantum computer is not far away from us. And without safe quantum safe cryptographic defenses, autonomous vehicles, military hardware, and online financial transactions and communications can also be targeted. So we should be worry about quantum computers and build encryption schemes in such a way that can prevent quantum, even if quantum computers comes into the picture. And quantum cryptography refers to the algorithms that will remain secure even against a quantum attack comes into reality. So currently there are a couple of techniques using which we can prevent quantum computers. These are lattice-based cryptography, multivariate cryptography, hash-based cryptography, code-based cryptography, and symmetric key encryption schemes that are like AES, where by changing bit size we can get the required security. However, most effort is going on in lattice-based code-based, and hash-based cryptography techniques for quantum world. Lattices are fundamentally important in optimizations and is known to cryptographers for long. Also, code-based cryptography, code-based systems are also used in error correcting codes, which can be which is extensively studied, like hash-based techniques. And in lattice-based cryptography, it is known that to compute the hard problem, which is also known as shortest vector problem, for large dimension, it is extremely hard. Also, lattice-based cryptography provides first quantum safe fundamental primitives, and which makes it the front runner in building quantum safe cryptography. Also, also progress has been made that TLS for TLS and internet key exchange protocols, lattice-based primitives have already been plugged in and also been tested. So, and not only that, lattices can also be used for different applications like integer programming with constant number of variables, polynomial factorization, and homomorphic encryptions, and cryptanalysis and designing of encryption schemes. Thus, lattices plays a very important role if quantum computer comes into picture. So in the next slide, I will be discussing about lattices, what exactly lattice is, and the basics of the lattices. Then after that, I will talk about our works. So, the first question comes to our mind, when we talk about lattices, what exactly is the lattice? So a lattice can be defined as a set of points in n-dimensional space with a periodic structure. Here are two diagrams. In the left diagram, there are two lattices which expands the two-dimensional space. The first one is represented by black, and second is represented by blue. The first one, each of these vector is known as bases. The first basis is, we can say that B1 is 1, 0, and second basis vector is 0, 1. And the second, the vector that expands the same lattice is B1 prime, which is 1, 2, and B2 prime, which is 1, 1. However, the figure in the right side is only expands sublattice of R square, because all the points using these two basis vectors, we cannot go to all points present in that grid. Now, from that, it's clear that changing basis vectors, an entire new lattice can be obtained. So in this example, I can these two in this example, the first diagram, there are two basis matrix vectors, black and blue, which expands the same lattice, but they are related. To show that relation, we can write b1 as b2 prime minus b1 prime, and b2 as b1 prime minus b2 prime. In short, we can write this one as b1. We can write in the matrix equation as b1 b2 equal to minus 1 to matrix minus 1 2 1 minus 1 and b1 prime b2 prime. Here the matrix the matrix minus 1 to 1 minus 2 has determinant of minus 1. That means whenever we multiply a basis matrix with a unimodular matrix, then we'll get a different basis matrix basis. So now what exactly unimodular matrix means is the matrix which have determinant of 1 or minus 1. So and a basis is said to be good or bad based on the how short the basis vectors are and how orthogonal they are. So if they are short and nearly orthogonal, then we say that basis as good basis. Otherwise, we will say it as bad basis. So this is an example of good basis and bad basis. In this example, the red two vectors which are shown in red are nearly orthogonal and short, so it is known as good basis. While the one with green color is quite large, quite large and not orthogonal, so this is known as bad basis. So now let's give a definition. Let's understand basis by definition. So about lattice by definition. So a lattice can be represented by a set of n linearly independent vectors b1 to bn, each of size m. That means to each of these vectors there are n number of elements, and then the lattice is generated by summation of multiplication basis vectors multiplied with integer elements z into b1 plus z into b2, like that. So here, and we can also write in summation format as xi bi, where xi belongs to z. This xi always needs to be an integer value. Then only we will get a basis. Equivalently, we can define this basis matrix in matrix form. B as m cross n matrix with b1 to bn as basis vectors. Basis vectors, and represents the column of the lattice generated by B. And we can write this one as lattice generated by basis B1 to Bn as B of B into X, such that X belongs to n dimensional integer. And dimension of the lattice is the number of elements in a basis, and rank of a lattice means the number of lattice vectors we have. In general, in lattice cryptography, we have m, that means dimension greater than rank. And whenever rank dimension is equivalent to rank, then we say it as full rank lattice. So, so as we have already discussed, if dimension is greater than equal to 2, then we can get, for the same lattice, we can get infinite number of lattice bases, because we can, by multiplying with different unimodular matrices, one lattice can be converted into different lattice. And determinant of lattice is just computed by determinant of lattice is just computed by computing the determinant of basis matrix. Now, modular matrix plays an important role in cryptography. So here, each element for a vector x or basis vector x that is generating lattice L, then we can write this one is x mod q to get modular lattices. That means if we have a matrix B, for mod q rank n and dimension m, then we can define n dimensional q array lattice as y equal to b transpose s mod q for some secret value s. So we have talked about lattices so much, but we have not yet discussed hard problems of lattice cryptography. So in lattice cryptography, there are two hard problems. One is a shortest vector problem and another is closest vector problem. So shortest vector problem says that given a lattice basis, you have to find the shortest vector present in that basis. And closest vector problem is given a lattice point in that lattice, you have to find the lattice vector lattice point closest to that given point in the given lattice. So there are different variants of these two problems. One is learning with error problem, which is the most famous in lattice cryptography. This is a sort of shortest vector problem, boundary distance decoding problem, small integer problem, shortest independent vector problem, shortest integer vector problem. So in the next, I'm not going to talk about shortest vector and closest vector problem in depth here. Rather, I will directly talk learning with error problem because it plays a very important role in designing cryptographic encrypts and schemes that are secure under quantum computers, and also it finds applications in homomorphic encryption schemes. So learning with error problem is nothing other than learning with noise, but with large modulo Q value. And there is another variant of learning with error problem, which is known as ring learning with error problem, and it's a ring variant of learning with error problem. Most of the post-quantum secure cryptography scheme uses more ring learning with error problem to design. And there are two variants of learning with error problem. One is search LW problem, search learning with error problem, and another is decisional learning with error problem. Now let's go to the definition of LW problem. So LW problem, in LW problem, we are given NQ, where N is a positive integer, NQ are positive integers, G is probability distribution on Z, S is a secret vector of dimension N taken from modulo field Q, and L of SG is a probability distribution sampled as Z and Q cross ZQ, ZQ. As AB, where A is chosen from Z and Q, that means A is a vector of length N, where each elements are chosen sampled with respect to Q, and then B is computed as A multiplied with S. A is Z and Q, S is Z and Q multiplication of this one plus some error term added with AS. So it gives us AB. And in decisional LW problem, now I will sample A and B the way we have shown here. By that means A and AS plus E, and another sample AB, which is completely sampled uniformly at random from Z and Q. Now we have to distinguish these two samples, and this is known as decisional problem. Decisional means you have to decide whether it's taken completely randomly from Z and Q, ZQ, or it's taken from distribution L of SG. And such LW problem says now given you are given A and B, where B is computed AS plus by doing AS plus E. You have to find out the value of S. And in literature, it has been shown that if we can solve one problem, then another problem can be solved. So here in the earlier slide, we have talked about the error distribution G, but error distribution G. In error, the error distribution usually is taken from normal discrete Gaussian distributions with mean 0 and standard deviation Q by NC. So since this error is chosen from discrete Gaussian distributions, that it have to be bounded within given standard deviation. Thus, LW problem is also known as boundary distance decoding problem or BDD problem. Now we have talked about abstract values for M and NQ. We have not given any concrete values for these values, these parameters. Now in this slide, I am going to give concrete values for N, M, and Q value Qs. So if we choose M equal to 640, N equal to 256, Q equal to 4093 in LWA problem, then it gives us security equivalence of AES 128 bit in the post-quantum world. But the problem here is that if we choose parameters values like that, then total key size becomes our 246 kilobyte. So 246 kilobytes. So this is one problem of LWA problem. However, using RLWA problem, the significantly key size can be reduced. There is also another variant of LWA problem, which is also known as binary LWA problem. Here, the key other than the key, everything remains same. Only the key becomes, that means secret S becomes binary. And if we choose secret S as binary, then we have to change our total number of these dimensions for the secret as 440 to keep same security equivalent to that of LWA problem, LWA and LWA problems n equal to 256. So I am not going to cover learning with error problem. Rather, I will directly go to Galbraith's versions of LWA problem. So Galbraith suggested to use binary matrix A and secret and binary secret S for low storage devices, so that the storage cost will be small. In Galbraith's binary LWA problem, we don't have to store matrix A or public key matrix A. Only storing the seed of 256 bit, we can later on generate the public key matrix A, and for that, so we don't have the space requirement for this Galbraith's binary encryption. Galbraith's binary LWA problems is this one 256. That means we have to compare store the seed value plus 640 into log of 4090, which is for storing the B value. So as a whole, we will be requiring 7935 bits, and which is approximately 1 kilobyte in compared to large key size of LWA problem. So now, so we have talked about LWA problem, and it's one drawback of a large key size. Now I will cover the attack techniques that are available in the LWA problem. So there are three attacks available to solve LWA problem. First is solving BDD problem. Then next is SIS problem. Solving SIS problem, we can solve LWA problem. Third is bidirectly secret recovery problem. So out of these available techniques, solving BDD is easy. Significantly easy compared to other problems. So in the next slide, I will be talking about attacking LWA problem using BDD, and we will be also using this technique in our work. So I will cover this in the next couple of slides. So to solve the LWA problem using BDD, solving BDD, we require to use Babay's nearest plan algorithm, and Babay's nearest plan algorithm solves the search LWA problem by finding sort vector E such that it satisfies AX equal to B minus C. That means whatever error we have added to get LWA problem, we subtract that error, and we will remain with the exact value of B, and using the linear algebra we will solve the unknown value of X. So in this way we will find out the value of unknown vector X. Here the E is sampled from Gaussian distributions, as I said earlier. All the noise is bounded, so all the error will be bounded by a small multiple of standard standard deviation. Usually 3, if we multiply standard deviation by 3, then 99.9% of the error lies within this interval. So a lattice is defined by columns of A, and B is the point within the boundary distance from the lattice, such that W equal to A into S. And in our case, we are going to solve BDD problem in the for the lattice point W, which can be later used to solve for S. Now, so we have mentioned the techniques to solve a BDD problem, but for that we have to have a good basis. That means the basis vector should be small. It should be nearly orthogonal. These vectors should be nearly orthogonal. To obtain that, we have to use lattice reduction algorithm, which is usually used to find basis with short and nearly orthogonal vectors. And to find short and nearly orthogonal vectors, there are 3 techniques available: LLL, BKG, and BKG 2.0. However, there is a trade-off between runtime and output quality of the reduced basis we obtained. If we want high quality output, then we have to run it for exponential time. Thus, to solve approximately solving LWE problem with some approximation is only possible. We cannot solve all LWE problems because we cannot tolerate high computation time. And so this so the quality is defined. The quality of the output or reduced basis is defined by orthogonality defect, which is just computed by this formula, and is this formula delta of B equal to multiplication of all the basis vectors divided by square root of determinant of B dot B transpose. Usually this orthogonality defect is greater than equal to 1. And after finding these after converting basis vectors into good basis vectors, we later on use nearest plane algorithm, and this algorithm is simple and runs in polynomial time. The algorithm and solves given a basis vector, y in the lattice and a basis b. The LLL this nearest plane algorithm gives solves the problem with approximation. So given a reduced basis for lattice B of n dimension and target vector T, we can find a vector B in such a way that it satisfies T minus B less than equal to 2 to the power n by 2 T minus U for all U belongs to lattice vector. So that this means with some approximation only we can this nearest plane algorithm can find out the exact nearest lattice point. And this problem can also, this approximation algorithm can also be used to solve closest vector problem. But we can, with some approximation only, we can solve the closest vector problem. Solving closest vector problem exactly requires exponential time. Now let's so yeah, this completes my lattice part. Now I will go towards homomorphic encryption. So as you know, encryption schemes are used to protect data breaches, but there is one encryption schemes that can also be used for private search, encrypted database query, secure cloud computations, etc. And to do all these operations, the encryption schemes have to satisfy if I perform some function on message M, and if I get the output f of M, and if same message is encrypted to obtain encryption of M, and the same function if I evaluate now in the encrypted domain, it should be equal to encryption of f of M, or it should be equal to encryption of f of M, and if I encrypt the f of M, then it should be equal to f of M. That means that means the function, whether it's whether the function is computed in the encrypted domain or the plaintext domain, it should be same. That means the output of the decryption of the output of decryption of the output that we obtain after computing in the encrypted domain, it should be same as the output we obtain after computing the same function in the plaintext domain. So, and this kind of encryption schemes are known as homomorphic encryption schemes. So homomorphic encryption schemes can be categorized into three categories: partial homomorphic encryption scheme, somewhat homomorphic encryption scheme, and fully homomorphic encryption scheme. Partial homomorphic encryption schemes only provide one operations, addition or multiplication. Most familiar example of this type is failure encryption scheme. And somewhat homomorphic encryption scheme provides both addition and multiplications, but limited number of times. And fully homomorphic encryption schemes provide all type of operations, unlimited number of times. So from this diagram, it seems that the fully homomorphic encryption scheme should be the best, but it's not the case. Bootstrapping operations is usually used to convert somewhat homomorphic encryption scheme into fully homomorphic encryption schemes. And after performing each operations in the ciphertext domain, we have to perform bootstrapping operations. And the cost of the bootstrapping operation is 139.8 seconds, and the key size is also 20 MB. So for practical applications, we cryptographers usually use somewhat homomorphic encryption schemes. But whatever encryption schemes available in the literature, not all provide the same level of security as they claim. So security of these encryption schemes needs to be revisited. So now I come to my work, my PhD work. So in my PhD work, we have performed cryptanalysis of 4 encryption schemes. Out of these 4 encryption schemes, I am going to talk the first encryption schemes, which is the space efficient version of the encryption scheme proposed by Galbraith. So yeah, we have talked about, I have talked about LWE problem and its related information, related topics, but I have not mentioned anything about how encryption is done in using LWE encryption scheme. In LWE encryption scheme, to encrypt a message M. So for simplicity, I have considered the message is 1 bit, but modifying this encryption schemes or the technique we do encryption, we can make it, the message can also be made to word. Here nonce to encrypt a message M, a nonce of binary layer of a nonce of binary of length M, a nonce vector of binary with content binary of length is sampled, and ciphertext C1 and C2 are computed as C1 equal to U transpose A, C2 equal to U transpose B plus message into Q by 2. And decryption is done by just subtracting C2 minus C1 S. So to attack this encryption scheme, we have to figure out the nonce. And if we can figure out the nonce, then because B is public, so and C2 is public, so just subtracting C2 minus U transpose B, we can find out the message M, encrypted message M. So thus we can say that recovery of nonce implies breakage of the encryption scheme. So here, yes. So in Galbraith's encryption scheme, the matrix A is used is binary. So we have a matrix of 256 into 640 dimension, and each of these contents are binary, and Q is of value 4093. So mod term will never be applied in the encryption this C1 computation. In C1 equal to U transpose B computation, mod value will not be applied because Q value is 4093 and content of dimension of A is 256 in 640, and each of these elements in of matrix A is binary. So it makes the value can be 640. So mod never gets applied. So ultimately, we are saying that if you can solve AX equal to B problem where dimension of X A equal to 256 cross 640, then the encryption scheme can be hacked. So, and we can also say that this is an underdefined system of linear equations with variable to equations ratio of 2.5. So now naturally one question comes to our mind is how hard might be the problem. So to show that the hardness of this problem, we have plotted this graph varying the number of equations, keeping the variability equation ratio constant of 2.5. And all computations are done in MATLAB 2015 B Intel i5 4 Gen with 3.65 gigahertz clock, 8 GB RAM, 16.04, 64-bit long LTS system. Here, as you can see, as the number of equation increases up to 50, we can solve within few seconds. But whenever it surpasses 50, the time for solving this exponentially increases. And this I am talking about. This figure is plotted for average time. So it doesn't mean that if I have a instance of 70 cross 70 into 2.5, then it cannot be solved within a few seconds. There might be some few instances that can be solved within few seconds, but more on an average, most of the instances are quite hard and takes hours. Now this figure is plotted for only dimension up to 70. Now we can imagine how hard the problem might be if we increase the number of equations to say 256. Yes, 256. So to solve this problem, we have used different techniques, but the one which is a hybrid of linear programming, lattices, and AI techniques gives us the highest success percent. So in our thesis, in my thesis, we have used a linear programming as a black box, which on input A and B gives us the output X, and it can be represented like this. The output will be of this kind, fractional values, and the red numbers or fractional values over here represents the incorrect output that we get when we run LP. So whenever we round these values, so 0.992 will round it to 1, but it actually should have been 0. Similarly, 0.49 should have been 1, but when we round, considering 0.5 as our rounding threshold, then it will go to 0, but it actually should have been 1. So this way, with few incorrect bits, we'll get LP output. So this is the bar diagram which shows the number of errors that we get whenever we solve this problem using linear programming. So whenever the values, the LP output gives us near to 0.5, these bits contains the highest error, and whenever LP gives us values near to 1 or 0, they have small errors. So this figure shows that. So yeah, so the next thing is that if we can remove 280 number of bits and use ILP, then ILP completely solves that problem. But removing 280 number of bits and solving using that ILP takes billions of almost around billion year to solve each instance, or try 280 combinations and use ILP. But if we can use lattices, then that number of guessing of bits gets reduced. So there is a trade-off between number of bits to remove and success. Yes, and removing 230 bits in removing 230 bits gives us the almost 100% success in case of lattices, while it is required to remove 280 number of bits in case of ILP. So now the question comes how to convert this problem into lattices. So we have AX equal to B problem. So we apply first LP, then sort the output and remove W bits with error E1. Then to the reduced problem A2 X2 equal to B prime, we apply LP, then we will sort the output, and as a whole we need to remove 230 number of bits. In the first step we have removed W bits, so in the next step we have to remove 230 minus W bits. So we partition, the first partition will be 230 minus W bits, second partition will be 256 into 256, and third partition will be 154. this 154, and we will try to remove 230 minus W bits with error A2. So if we partition like this with this values, then it will be A21 Y1, A22 Y2, A23 Y3 equal to B prime. Now just using simple linear algebra, we will obtain A22 inverse A23 Y3 approximately equivalent to A22 inverse B prime minus A21 Y1. So here approximately we have written because here Y2 value we have subtracted the LP output value. So in that LP output value, only very few number of elements, elements will be incorrect. So only very few will be incorrect. So we can write it as an approximate value. So now here, so the inverse here we have considered is of mod inverse. To compute the inverse, we have used a modular field ZQ, where Q equal to 29 bits. This is an experimental parameter, and 230 number of bits is also an experimental parameter. So for correcting, and now to correctly get the Y2 value, we'll solve boundary distance decoding problem with lattice as A22 prime inverse, A23 prime, and lattice as this one, and the basis, the destination vector as A22 prime inverse, B2 B prime minus A21 prime Y1 prime as my destination. Now the next thing is that we can remove 230 bits in a single go, or we can also remove in double steps. So this is the plot which shows the advantage of removing 230 bits in double steps in comparison to single step. If we so in the figure, the labels below the figure 0, 1, 2, 3, it represents the number of errors we are covering, and the bar represents the number of instances that gets succeeded. If we remove so here, orange color represents the before LP number of bits removed, number of instances that gets succeeded before applying LP, covering say certain number of errors, and the blue line represents the number of instances that gets satisfied by covering few certain number of errors. So as you can see from this figure, that covering very few number of errors after applying second LP, we can succeed in more number of instances. And the partition means a tuple. Partition is a tuple of P, W, E1, and E2, and that here the partition we have used is P equal to 0. That means starting from 0th position, we have removed W number of errors, which is 175, and after removing 175 number of bits, we will again apply LP and sort that output again, and 230 minus 175 number of bits will remove, considering say few number of errors, which is decided based on our computation facility. And yeah, partition is defined by P1, E1, E2, and yeah, and a partition's computation time is decided by this one formula. LP, first we apply LP, then we will try all these combination W minus E1 number of combinations, and to each of these combinations we will apply LP again. Then to each of these combinations we apply lattice reduction, and remaining 230 minus W bits we will remove. We considering E2 number of errors, and to each of these combinations we will apply Bombay's algorithm, and to get the correct value. And these are the few runtime. These are the runtime of the algorithms that we have used. LP implemented in MATLAB takes 2 seconds. Similarly, Bombay and BKG takes 0.2 and 9,000 seconds. Now we have so here P, W, E1, and E2 everything can vary. Now how to identify a good partition? That's the huge question. To identify to solve that question, we have used training and testing. For training, we have created 10,000 instances, and now we term as the number of instances that satisfy a particular partition. We term each success of that partition, and these are the a few success percent that we have obtained considering 1000 number of cores. Here P means P for the partition P equal to for 40 120 33 we get total success percent of 3.39 within 169 days and so forth. Now we have these many partitions. So we have this kind of lots of partitions. Now these are the distributions of these different partitions. These are the frequency of different partitions. What kind of partitions lies in where? So here we can say that whenever we get success percent greater than 3, then the partitions are very less. However, if the success percent we give, the partitions which gives us success percent nearly greater than 1.5 are very high. So we have lots of partition in this way. Now, how to identify good partition? To solve that problem, to handle that problem, we have used budgeted maximum coverage problem. A budgeted maximum coverage problem gives gives us a greedy solution, which is 1 minus 1 by E of the optimal solution. And this is the output output that looks like when you use a budgeted maximum coverage problem. The different partitions that is selected by budgeted maximum coverage problem to get high success percent. And this graph shows the different success percent of different algorithm we have used. The last one represents the application of 1LP and ILP success percent using 1LP plus ILP. Blue one represents 1LP plus lattice. The brinjal one represents 2LP plus lattice, and the last one, red one, represents 2LP plus lattice plus AI training and testing concept. So from this we can say that whenever we use 2LP plus lattice and AI, we get the high success percent. And the behavior of this technique when we use for different dimension the problems, keeping the number of equations constant as 256 and varying the number of variables. For 640, it's quite less, but whenever the number of variables decreases to 620, we get a little bit higher success percent. For 600, we get kind of good, and for 580, we get almost very good success percent. And so now concluding my this talk, we will say that post-quantum computers are future reality, so more energy should be invested in post-quantum cryptographic research, and also through a study of the post-quantum skills is needed for security and efficiency purposes. Thank you. I will conclude my talk here, and these are the few references. Yes.
Okay, any questions from the audience? One thing, like Tikaram, can we have you shared these slides anywhere that I can share with people, or
no?
Okay.
This I have specifically prepared these slides for this talk only.
Okay. So anyhow, what we'll do is we'll anyhow put the complete video on the site. So anyhow, like if people are interested in the content, they can anyhow get it, right? So
sure.
Right. So are there any questions, or shall we just conclude? And I guess we can conclude. It's already actually 8, and we started very late today, and it has gotten later, right? So thank you, Tikaram. Thanks a lot for sharing your precious time with us, and giving us a view of what the world, which kind of looks both scary as well as exciting, that we are actually moving into the world of quantum computers. There are certain nice things that we can get, as you predicted, right? You can probably start predicting traffic jams before they occur, but at the same time, all of our cryptography might go into the bin. We have to reinvent everything, to be honest, right?
Correct.
Right. Okay. So yeah, thank you, Tikaram, and thank you everyone who joined us so late in the evening. And we'll actually be putting this talk online anyhow on the YouTube channel of IITISM. So Thanks anyone. Thanks everyone. And thank you, Tikaram, again. Thank you.
Thank you, Professor Saurabh, for providing me such an opportunity to present my research work. Thanks.
Thank you. Thank you, guys. Thank you, everyone. Bye.
Thanks.